An airport lounge often has large open spaces to make it easier for passengers to move around and also to facilitate security. Now, one way to achieve this is to use a lightweight roof truss which provides a large span and a very strong structure. Achieving this objective requires an unusually extensive roof span, and this means a very lightweight roof with a high span-to-depth ratio. Here at Manchester Airport's Terminal 2, the architects have used the so-called space frame structure. It's light, airy, and aesthetically pleasing, and they've even echoed the structure in the decoration. The space frame structure used here as a roof truss is of interest to the mathematician because it's constructed from a small number of modular components which are assembled into a regularly repeating arrangement in space. The framework's constructed from modular components forming a repeating pattern in three-dimensional space. If you look at it from various positions and along different directions, you can see how the struts and joints line up, rather like the trees in an orchard. If you look closely, you can see that there is just one type of strut and just one type of joint. This architectural system is based on a unit shape made from one regular octahedron and two regular tetrahedra. Naturally, it's known as an octet truss. And this is just one of the many ways in which three-dimensional space can be filled with repeating polyhedral unit shapes. In this video, we're going to explore the mathematics behind the idea of filling space. We'll also be looking at how the mathematics of space fillers links with the mathematics of three-dimensional packings. Let's begin by taking a closer look at the kind of octet framework we have here. The octet configuration of struts and joints is often attributed to the architect Buckminster Fuller, who is more commonly known for his geodesic domes. But in fact it was in use earlier. At the start of the 20th century, Alexander Graham Bell employed the octet framework when he was trying to construct very strong, rigid, lightweight kites as part of man's first attempts to fly. A kite is a bounded object, and so its framework is necessarily of finite extent. But the true octet system extends indefinitely, in three independent directions throughout three-dimensional space. Both the tetrahedra and the octahedron making up the octet unit are themselves naturally rigid, and so this rigidity will not be destroyed if the octet unit is repeated throughout space. But there's a problem with using a framework made from complete octet units. Most buildings are rectangular in plan, with right angles between adjacent walls. Roof trusses have to conform to this rectangular geometry. You should also be able to pick out several planes at various angles. This one, for instance, shows hexagonal symmetry where 6 struts meet at each joint in the plane. Other planes, which are horizontal, have square symmetry, and there you have 4 struts meeting at each joint. By slicing it like this, we get a two-dimensional slab made up of square pyramids and tetrahedra, sandwiched between a top and bottom plane surface. But actually, each square pyramid is just half an octahedron. If we try to complete each octahedron with another square pyramid to form a second layer, we get this arrangement. Unfortunately, not only have we doubled the thickness of the roof, and hence almost doubled its weight, but we have created more incomplete octahedra. Adding a further layer would have the same effect. Whatever we do, we can't complete the octahedra. So although we can think of the roof as being made up from square pyramids and tetrahedra rather than from octahedra and tetrahedra, if we want to think of one unit repeated so as to fill three-dimensional space, then a more natural unit is the octet. But do architects have to spoil the simplicity of the octet arrangement in this way? Looking at the walls of this building, we can see that here the architects haven't entirely been constrained by the usual rectangular geometry. Here the three-dimensional octet framework has been sliced at a different angle to produce this slab. Now there's a true octet arrangement consisting of complete octahedra and tetrahedra in the ratio of 1 to 2, and no other polyhedra. And this time we get either triangular or hexagonal shapes, rather than rectangular ones. So this octet space frame forms a powerful modular construction system designed by architects and civil engineers. But as usual, nature got there first.
This honeycomb provides a safe nursery environment for the queen bee's eggs. Worker bees construct the comb out of beeswax in the form of a regular array of adjacent cells. Evolutionary forces have favoured this particular arrangement because it requires a relatively small amount of wax to enclose a large number of cells. The ratio of cell surface area to the volume of the cells is almost the smallest possible. Now, you might think that the cells are hexagonal prisms, but let's take a closer look. In fact, the cells form two layers, with the hexagonal faces of one layer centered directly over the vertices of the hexagons of the second layer. So, does that mean that the honeycomb is a two-layer staggered arrangement of hexagonal prisms? Let's take a look from the side. In fact, what look like hexagonal prisms don't have flat hexagonal bases. In reality, each base consists of 3 rhombuses, with each pair meeting at an angle of 2 pi by 3. So the cells are actually rhombic dodecahedra. The hexagonal prism effect is achieved by slicing. And here we're slicing the rhombic dodecahedra by a plane, forming hexagonal cross-sections. So the bee's honeycomb is really a double layer of rhombic dodecahedra, rather than hexagonal prisms. But unlike the bees, we don't have to stop at 2 layers. Any number of layers of complete rhombic dodecahedra can be stacked to extend indefinitely throughout 3-dimensional space. This arrangement provides the bees with a relatively secure hive constructed with almost minimal resources, yet it still allows easy access to each cell.
We've now looked at 2 different systems of polyhedra, the octet truss and the honeycomb. In both systems, the polyhedra fit together in face-to-face contact and they fill 3-dimensional space. And additionally, they both possess cubic symmetry. So is that all they have in common? Well, they do look very different from each other, but there is a relationship between them. Perhaps surprisingly, they are space jewels of each other. The vertices of the octet lie in the centers of the rhombic dodecahedra, and vice versa. You may find these structures and their relationships easier to understand after you've tackled the activity in the audiovisual notes. So far, we've seen how architects have used the octet as the basis of Terminal 2 at Manchester Airport, and how the bee's honeycomb uses the space jewel of the octet, the rhombic dodecahedron. Yet another space filler has been used here in this experimental, self-contained habitat known as the biosphere. There are many examples of other space-filling systems, both natural and man-made, but let's look first at probably the simplest way of filling space, with identical cubes.
Is it the same?
I'm sure most of us played with wooden blocks as children, for instance. And here the cube is being used as the basis of a piece of sculpture. Generally, cubes are in face-to-face contact with no overlaps, no intersections, and no spaces or holes left between them. A face of one cube exactly matches the face on an adjacent cube, and the arrangement can be continued indefinitely in any direction. The cube is a polyhedron which fills space. We're calling a unit like this a polyfiller. In particular, this is a cube filler. Other types of space filling are possible, such as the way these bricks are stacked and interleaved. But in this arrangement, the faces of the cuboids overlap. And in this video, we'll ignore this kind of space filler. Instead, we'll restrict ourselves to polyhedra in face-to-face contact. Essentially, the three-dimensional analogues of two-dimensional tilings. So, what else is possible in 3 dimensions? You may remember that in 2 dimensions, if we restrict ourselves to either regular or semi-regular tilings, then there are only 11 possibilities. Here we've got the 3 regular tilings and 3 of the 8 semi-regular ones. Similarly, in 3 dimensions, there are only 23 possibilities, based on regular or semi-regular polyhedra. Let's see if we can generate some of these by transforming the cube.
One of the simplest ways is to start with the square tiling in 2 dimensions. And think of the cube as a square which has been extruded in a direction normal to its plane, to produce a square prism. The cube filler consists of layers of these extruded square tilings stacked on top of one another. But we don't have to restrict ourselves to square tilings. The same process can be applied to the other 2-dimensional regular tilings. We get 2 new polyfillers, the triangular prism and the hexagonal prism. And in fact, we could perform the same extrusion and produce polyfillers from any of the remaining 8 semi-regular tilings that you met earlier in this course. Another way of generalizing the cube filler is by applying linear transformations, scalings, or shearings, for instance. These change the cubes into congruent parallelepipeds. Do any other variations of the cube still fill space? Well, another thing we could do is divide up the cube filler into a number of parts, and then recombine the parts as new polyhedra. For example, if we join the centre of a cube to each of its 8 vertices, we divide the cube into 6 square pyramids. If these are combined with ones from adjacent cubes, we get octahedra. All of the cubes have been replaced by octahedra. So we have another space filler using these octahedra. So does this mean regular octahedra can fill space? Well, no. These octahedra are space fillers, but they aren't regular. You might like to prove that these octahedra aren't regular for yourself after you've worked through this video.
Another very interesting way to generalize the cube filler is by truncating the cube. Again, let's see what happens in 2 dimensions first. Suppose we chop off the corners of each square at an angle of π/4. We are left with octagons, each in edge-to-edge contact with 4 neighbours, and square gaps. Filling these gaps with squares produces a tiling of squares and octagons. In 3-dimensional space, we get a similar result by slicing off the corners of the cubes. Each vertex is surrounded by 8 cubes, so slicing the corners off each of them will produce an octahedral whole. In other words, we are left with truncated cubes, each in face-to-face contact with 6 neighbours, and octahedral holes. So by filling these holes with octahedra, we produce a polyfiller combination of truncated cubes with octahedra. But does it matter where we cut off the corners? What happens if we go halfway along before we slice? In 2 dimensions, we just end up with a square tiling again. So do we end up with cubes in 3 dimensions? Well, no, we don't. This time, we end up with a polyfiller combination of octahedra with cube octahedra. Finally, here's another way of looking for new polyfillers. Earlier, we showed that the octet and the rhombic dodecahedron were space fillers which are space duals of each other. So what polyfiller will we get by taking the space dual of the cube? In the usual way, we get a dual by taking the center points and then joining pairs of center points with an edge, if and only if the corresponding polyhedra are in face-to-face contact. Finally, let's replace the original cube polyfiller with these new polyhedra. Well, as you might expect, we get the cube filler again, because the cube is self-space dual. But the idea of taking the dual can be applied to any polyfiller. We'll still end up with a space-filling system. And if the new space-filling unit isn't self-dual, then we've generated a new space filler.
In creating polyfillers, there are two main factors at work: symmetry and packing. Symmetry is a global feature, since it tells us about global appearance and behaviour. The symmetry acts on the whole of three-dimensional space. Packing, on the other hand, is a local feature. It tells us how the pieces fit together locally. For instance, the cube filling has cubic symmetry, as do the octet and the rhombic dodecahedron fillings. The fillings that use triangular prisms and hexagonal prisms both have hexagonal symmetry. These space-filling systems have translational regularity in three-dimensional space. So globally, each one must have the symmetry of the crystal systems that you've seen in the unit. But what about local behaviour? Let's recap what happens in 2 dimensions first. In this semi-regular tiling, we can easily see that adjacent polygons must be in contact along an edge. But if we look at a vertex, we can see that the interior angles of all the polygons meeting there must add up to 2 pi. Otherwise, there'd be gaps. It's a similar situation in 3-dimensional space. Not only do the contacting faces of adjacent polyhedra have to match, in other words, they must be congruent polygons, but the interior dihedral angles of all the polyhedra meeting at an edge must add up to 2 pi. For the cube filler, there are 4 cubes meeting at every edge. This filler works because the dihedral angle of each cube is pi by 2. 4 lots of pi by 2 add up to 2 pi. On the other hand, for the triangular prism filler, there are 2 different dihedral angles. Where 2 squares meet, the dihedral angle is pi by 3. Whereas where a square and a triangle meet, the dihedral angle is pi by 2. So when we look at how this polyfiller works as a space filling, we get 2 different types of edge. At a horizontal edge, where 4 prisms meet, we have 4 lots of pi by 2, making up 2 pi. But at a vertical edge, 6 prisms meet, and so this time we have 6 lots of pi by 3. So what happens with the octet filling?
We've seen that the octet filling works, but why? What is happening at the edges where 4 octets meet? Well, at an edge, we'll always get 2 octahedra and 2 tetrahedra. And the octahedra and tetrahedra alternate around the edge. Octahedron, tetrahedron, octahedron, tetrahedron. If we place just 1 octahedron with 1 tetrahedron, then their dihedral angles add up to pi. So 2 of each around an edge adds up to 2 pi. The octet truss fills space because if you fit 1 octahedron and 1 tetrahedron together, you get a flat surface. So 2 of each meeting at an edge fills space. But is this the only way we can arrange these two polyhedra to fill space? Well, no. You may have spotted that we could assemble a two tetrahedra and two octahedra in a different order. Instead of alternating them around an edge, we could pair them like this. Octahedron, the other octahedron, then a tetrahedron, and then the other tetrahedron. So does this new arrangement give us a new polyfiller? Do we get another unit that fills space? Well, yes, we must do. The new unit is another type of octet because it's made up of an octahedron and two tetrahedra again. But this new octet has hexagonal symmetry. Both types of octet occur as natural crystal structures. This octet, with hexagonal symmetry, is the arrangement in which magnesium atoms align themselves in a crystal. Whereas this octet, with cubic symmetry, is the arrangement which copper atoms prefer. Before studying the rest of this cassette, I'd like you to stop the video and do the activity in the notes.
When you see bottles packed into a box, they're grouped together in an arrangement which has to fit naturally into the cuboid box. The bottles are aligned in rows and columns along mutually orthogonal directions. But actually this is a rather loose packing arrangement, as each bottle only touches 4 neighbours. If the box is triangular in shape, we achieve a closer packing, one where each bottle touches 6 nearest neighbours. Some wine racks actually do store the bottles in this arrangement. This triangular packing is actually the closest possible for equal circles in 2-dimensional space. And for cylindrical objects, this packing also works in 3-dimensional space. But is there a closer packing with different shapes? With cylinders, each touches 6 neighbours on its curved surface, and possibly a further 2 neighbours in the layers above and below on its flat surface. This makes a total of 8 neighbours in all. But it is possible to have shapes that pack more closely. In this pile of apples, most of the apples have more than 8 possible contacts.
To make it easier to see what's going on, let's replace the apples with equal-sized spheres. We can assemble a layer in a triangular arrangement, just like the circles in 2 dimensions. What happens when we add the next layer of spheres? Each sphere sits naturally in a depression between 3 spheres on the bottom layer. When we extend the process across the second layer, only half of the depressions in the first layer are filled, as we can see from the 3 gaps. So what happens in the third layer? We've got the unfilled depressions in the first layer and the new depressions in the second layer. So we've a choice of where the first sphere goes, either in a depression like this or like this. What about the next sphere? Well, once we've decided where to place the first sphere, if I want the closest possible packing, the positions of all the other spheres in that layer are determined. For the third layer, we could place a sphere over a depression in the second layer, which lies directly above a sphere in the first layer, like this. The entire third layer now lines up directly with the first. But there's an alternative. The sphere could go over a vacant depression in the first layer. In other words, over the gaps. This third layer does not now lie directly above either of the first 2. So what happens in the next layer? Well, as before, there's a choice of 2 arrangements for the spheres. Which one depends on where we place the first sphere. But whichever choice we make, the first sphere must lie over either a sphere in the second layer, as here, or over one in the first layer. We can continue adding layers in this way to assemble a 3-dimensional packing. But because we have this 2-way choice at each layer after the second, there are an infinite number of different packings we could produce. Most of them, however, won't be regular ones. In this course, we've concentrated a great deal on symmetry. So a natural question to ask is, are there any packings which have any lattice symmetry?
In fact, there are two packings which have special importance because they have a simple repeating pattern. The simplest pattern is where the layers alternate in a sequence with period 2. The third layer is aligned with the first layer. Then the fourth is aligned with the second, the fifth with the first again, and so on. We produce a sequence of alternating layers. All the odd-numbered layers align with the bottom red layer, and all the even-numbered layers align with the bottom blue layer. So the sequence is red, blue, red, blue, red, blue, and so on. The other interesting example of simple symmetry is where the first 3 layers are all different, and then we repeat this sequence. So that layer 4 is red, like the first layer, layer 5 is blue, like layer 2, layer 6 is yellow. Then it would be red, blue, yellow again, and so on. This sequence has period 3. So we've now got 2 different closest packing schemes. But how close are they? If we took a central sphere, how many neighbours would it have in each scheme? Well, they're both equally efficient. In each of them, a sphere touches 12 closest neighbours. One way of looking at this is to think of 6 touching spheres in the horizontal plane, plus 3 forming a tripod above, and 3 forming a tripod below. But we know the 2 schemes are constructed differently. So how do they differ? Well, the difference is in the orientations of the 2 tripods. For the red-blue packing, the tripods are mirror images in the horizontal plane. But for the red-blue-yellow packing, the tripods are not. Instead, they are inversion images in the central sphere. If we look closely, we find that this packing has cubic symmetry. The centres of the spheres form a face-centred cubic lattice. In fact, this arrangement is precisely that of our original octet. But remember, there's another type of octet polyfiller. This is the octet with hexagonal symmetry. Here, for clarity, we've omitted the tetrahedra, so we're just left with a stack of octahedra. What kind of sphere packing do we get if we expand its joints? Well, we get the other packing, the one that alternates the red and blue layers.
We began by looking at the octet truss, and although it's used here in an airport environment, it's well and truly down to earth. But the octet is such a powerful system that it can cope with the demands of outer space. It's a space filler in more ways than one. This is a model of Space Station Freedom. It'll be assembled in orbit from space-filling units like the octet. And perhaps one day the idea of space filling will be applied to the building of something as fantastic as this. It's an idea for terraforming the planet Mars by literally turning it into a gigantic greenhouse.